Let's add some more tools to our integration toolbox. So there have been a few tricks that we've learned to integrate, and then we saw use substitution, which allows us to undo the chain rule. But otherwise, we're kind of limited in terms of the complexity of the problem that we can integrate. So we want to keep building on our skills so that we can solve more and more integrals. And so the next thing that we're going to look at is integration by parts. And this allows us to undo the product rule. The product rule, if we recall, states that if we take the derivative of two functions being multiplied to each other, u times v, we simply take the derivative of one, derivative u times v, and then we add to that, we leave the first function, we take the derivative of the second v. So take the derivative of one, leave the other, and then switch that, leave the first, and take the derivative of the second. So let's think about this with the integrals then. So if we were to integrate the derivative of that thing, then we could think about that as integrating this this product rule that we just stated. So we'd have the integral of u prime x v x plus u of x times v prime of x, simply the derivative of the thing that we just stated. And then we can always break up sums inside integrals. We can break that up into two different integrals. And then I'm going to do a little bit of rearranging here. I'm going to try to isolate this term right here, and I can do that simply by just subtracting this piece over to the other side. So if we were to take the integral of ux times the derivative of vx dx, that would be equal to the derivative of u times v minus the integral of v times the derivative of u. And this is what gives us our integration by parts formula. The integral of u times v prime dx is equal to uv minus the integral of v times u prime, because remember the integral of the derivative is just itself. That's our fundamental theorem of calculus. Or if we were to write this using the simpler differential notation, the integral of u dv is equal to uv minus the integral of v du. And so we're going to use this trick to help us integrate some other problems. Let's just jump right into an example so we can see how this is done. Let's take the integral of x sine x dx. And so what I'm going to do here is, right now we're thinking about starting with this left-hand side. One of these things is the u function, the function that hasn't been differentiated, and the other is the dv, something that has already been differentiated. And so what I want to think about is when I set my u, notice on the other side is what we're taking the derivative of, I need that to become simpler and simpler. I'm going to hope to pick a u function that when I take its derivative becomes simpler and simpler. The dv is going to be the more complex function in that we are finding its antiderivative, so it can't be too complex. It can't be something that we just can't take the antiderivative of, but it's something that would not have otherwise simplified by taking its derivative. So if we look at our problem here, let's choose it the wrong way around first. Let's say that we had chosen u to be equal to the sine x. Well, then du would be equal to cosine x. And notice how it's not really going away. It's not making this integral down the road any simpler. We would still have dv would be equal to x, and that means that v is equal to x squared over 2. We're making both of these functions, well, we're making one of these functions more complex, and the other's not really changing in complexity. So when we're to go set up that second integral, it's not helping us at all. So let's choose these, the opposite of that. Let's let u equal x, because when we take its derivative, it becomes just a nice simple dx. And let's let dv equal the rest, the sine x dx. And so that means that when we are to take this antiderivative, we get a negative cosine x. Okay, so we are setting half of this equation, or half of this integral here as our x, and the other half is the dv. We're taking the derivative of the x, we're taking the antiderivative of the dv. So then this integral here would have to be equal to u, which is x, times the v, negative cosine x, minus the integral of v, which is negative cosine x, times the du, which we found to be dx. So now that second integral there is much, much easier. We can pull the negative to the front, and now I can take the antiderivative of cosine x, that is simply sine x. And then because we've taken the antiderivative, but it was an indefinite integral. We need that plus c. So there would be our answer. That one was relatively simple. It had a simple u to choose because we can clearly see that x is going to be reduced each time. Let's do another example. Let's take the integral of the natural log of x dx. Now, this one doesn't actually even look like a integration by parts example. We only see one function there, the natural log. Natural log, we've never taken the antiderivative natural log if you think about it. What seems to be a relatively simple function, we've never talked about its antiderivative, and it's because it's more challenging than you would think. Now, the only function I see here is the natural log, and that's the more complex function because it's the thing we don't know how to take its antiderivative. What does that leave for the dv then? The dv is just simply the dx. So let's see where this gets us. du would be equal to 1 over x dx, and dv would be, the v would be just x then. We can think about the dv, the other multiplied portion of the function, as just being a 1 dx. And so that actually, when we take its antiderivative, it becomes a more complex function. It's gone from 1 to x. That seems like a bad thing, except for notice that the derivative of the natural log is 1 over x. So let's write this using our integration by parts formula. So we would start with the u times the v, which is natural log of x times x, minus the integral of, then we would have our v function, which is x, and our du is 1 over x dx. And so we'll have, I might just pull that x to the front so it looks a little bit nicer. The x times the 1 over x just becomes a 1. So we're left with the nice simple integral of dx, which we know is just x. And of course we need the plus c. And so to answer the question, what is the antiderivative of the natural log of x? It would be x natural log of x minus x plus the integration constant. So quite a complex function just to be left with the natural log of x. Let's take another example. So let's integrate integral x squared e to the 2x dx. Now, if I look at this, what should I let my u be? Well, I definitely don't like the e to the 2x because I know that anytime I take the derivative of an e function of any exponential function, it stays the same. It might add a little bit, but that doesn't seem like it's getting me anywhere. So I definitely want the v to be the e to the 2x because that's not going to ever simplify. Now what that means is I'm stuck with the x squared as my u. Now if I were to take the derivative of that, it becomes a more simple function. It doesn't disappear. So that might create, I won't say problems, but it might lengthen our process in this example. So let me shift these over a little bit just so I have a little bit more work to work underneath. So we're going to let the u equal the x squared and the dv equal the e to the 2x dx. So our du would be equal to 2x dx, and our v would be equal to e to the 2x over 2. Remember, we've got to have that chain rule there. If we were to take the derivative of e to the x, it does stay the same, but we have to multiply it by its inner function derivative, which is 2. So that would be our v. So now we can express this integral as the u, x squared, times the v, e to the 2x over 2, minus, and now we're going to have the integral of our v, e to the 2x over 2, times our du, which is 2x dx. And so if we clean this up a little bit, we'll see that the 2's cancel, but we're inside the integral, but we're still left with an x there. And so we still can't integrate this. This is still not a nice, easy derivative rule that we can undo. But it did seem like letting u equal that x squared got us somewhere. It got us to the reduced x. So what if we did it again? Let's do another round of integration by parts. Let's let the u equal x. Let's let the dv equal e to the 2x dx. The du would be equal to dx, and the v would be equal to, once again, e to the 2x over 2. So we'll have x squared, e to the 2x over 2, that's from before, minus, I'll put this in brackets so we can really see what's happening. The integral would become the new u, which is x times v, e to the 2x over 2, minus the integral of, now we would have our v, e to the 2x over 2, times the du, which is dx. And so we've simplified the inside of that integral. We also actually have a third term now. This x e to the 2x minus 2. I do have to remember to distribute the negative, so the x e to the 2x gets a negative. I also have to distribute it to the integral, so we have a plus there. And then I can factor the 1/2 out of the integral. We'd have e to the 2x dx left. And now that is a very easy antiderivative to calculate. So we would have e to the 2x over 2 once again, plus our c. And so we can clean that up just ever so slightly by writing that as an e to the 2x over 4. That'll be a plus e to the 2x over 4 plus c. And so there is our derivative. Our integral, our antiderivative. Notice that we cannot simplify any of these terms. We have the x squared, we have the x, and we have the constant, more advanced constant back here. All right, so let us move on to another example. Let's take the integral of e to the x sine x dx. Now what we saw in that last example is that we can apply integration by parts multiple times, and that is true however many times we want to do it. If we want to do integration by parts 100 times over, that is possible. If I were to have given you the same problem as the last one, but instead of starting with an e to, or an x, what did I start with, x squared, if I'd instead start with e to the, x to the 100th power, we would have to do a lot of steps of integration by parts, and that would be challenging, but we would get to the answer. It is absolutely possible. It'd be much more efficient to have a computer program run that for us, but that is the process for how we would do it. What if, though, it just continues to cycle? What if we were to continually do this integration by parts and we were to keep getting things that kind of look the same as where we started? Well, that might be valuable too. So let's think about this problem. We have e to the x times sine x. E to the x, I could take its derivative 1,000 times over, its antiderivative, and it's going to look exactly the same. Sine x won't look exactly the same, but it will eventually cycle back around to something that looks kind of like it. Sine x, the derivative of that is cosine x, or the antiderivative negative cosine x, and then it gets back to the sine by the next step. So let's try something. Let's let u equal e to the x, because if I were to take its derivative, me right back to where I was, e to the x dx. Let's let dv equal sine x dx. That would mean our v was equal to a negative cosine x. And let's try to set this up with our integration by parts formula. So using integration by parts, we'd have our u e to the x times our v, which is negative cosine x, minus the integral of our v was negative cosine x, and then our du was e to the x dx. Doesn't seem like we've made anything any better here. We've gotten some stuff out of the integral, but the integral itself that we're trying to solve now is just as complex as where we started. It's a cosine now instead of a sine, but otherwise it's just the same. Let me go ahead and do a little simplification here before I move on to the next step. So I'm going to multiply these first two, just bring the negative to the front, and then bring the negative to the front on the integral as well. So we'd have e to the x cosine x, just so it makes it look even more similar to where we started. Didn't seem like it got me anywhere, but let's try it again. Let's see. So let's let u equal to e to the x, dv is equal to cosine x dx. So our du is equal to e to the x, and then v is equal to sine x d. Don't need the dx here anymore, just sine x. And so we would have the negative e to the x cosine x that we had from before, plus the integral. We can write it as e to the x sine x minus the integral of sine x. I mean instead of a dx with it, e to the x dx. And so we've gone right back to where we started, and that seems like a bad thing, but it's actually not. Because remember, what we have here is an equation. And so let me try and squeeze this in. I should have left myself a little bit more room, but I'll see if I can squeeze it in. Remember, what we are saying is that we have the integral e to the x sine x dx equal to this other thing on the right-hand side. This is an equation. These two sides are equal to one another, which means I can move things around the two sides. So because we have the exact same terms on both sides, we have this thing right here in green, we have this thing right here in green. Let me take this right-hand side and add it over here to the left-hand side. That would mean we would have two integrals of e to the x sine x dx is equal to a negative e to the x cosine x plus e to the x sine x. And if I want to know what this integral is right here, well, I have an equation that's nearly there. It just has a 2 with it. And so I need to divide off that 2, and I'm going to have my answer. E to the x sine x dx is equal to negative e to the x cosine x plus e to the x sine x over 2. And that's all I have. That is our answer. So it's kind of an interesting process where we're using the formula, but we're not just kind of forgetting about that left-hand side. We're not just forgetting about where we started like we were with the earlier ones, right? Here we just kind of ignored it. We said, all right, let's keep breaking it down, keep breaking it down. But now here we're saying, remember, it is an equation. This side is equal to this side is equal to this side is equal to this. And so once we have that same term on both sides, we can add it over, and we can divide off that piece that we didn't want to get the integral that we wanted. Now, I have been a little bit sloppy on all of these. Really, when we go from this first line to this second line, we are doing some integration, which means I need a plus c here. And then when I go from, let me keep track of it, plus c here. And then when I go to that next step of integration, I have another plus constant. I'll call it plus d. So this whole time we've had a constant of integration. We really now have a c plus d. But what I can do is I can just wait till the end and stick it back on. It's, like I said, a little bit sloppy. We're kind of leaving it for a little bit. But I'm going to stick it back on at the end as just a plus c. You might say, well, didn't you add the plus c here? But remember, c is just a placeholder. It is a fixed number depending on what the initial conditions are. But because we haven't assigned it any value, I'm just going to use the c to represent the terminal number. I could also call this c1, and then d, c1 plus d would be equal to our final c. But we're doing the same thing in all of these. Really, every single time we are dropping that integration sign, we have integrated, we need a plus c, and then here we need another plus c, and then by the time we get to our final example, or our final answer rather, that terminal c would be equal to the earlier constants that we had added. So integration by parts does not work for every single example. It is only when we have these narrow conditions that when we take the derivative of half of that product, we get a more simple function, or if we were to take the derivative and integrate, we're going to get back to that initial integral that we had in this example. So it is related to the product rule. We do have to have some sort of product rule there. Is it going to work on every single one? No, that is why we have a number of tools at our disposal for integration.